Let's start about classification of the cations here. How do we identify uh, various ions using this wet test? Mainly, cations are classified into five groups on the basis of their precipitation with some reagents. And the classification is based on whether a cation reacts with this reagent to form precipitate or not. That is Ksp value differences or the solubility differences. Now, this group 0 and group 6, if you compare, they particularly don't have multiple number of cations. They have only one particular type of cations here. Check. When it comes to group 0, that means you are only identifying for NH4 plus. And group 6, here, since there is no group reagent to make any precipitation, we are clear that we are trying to figure out whether it is magnesium 2 plus, Na plus or K plus. Correct? What is the procedure that we do here? You know, what we, once you take a salt here, correct? The first thing we will try to do is dilute this salt with some water. Okay? If water helps in dilution, that is good enough. If not, if you are analyzing group 1, you would add some amount of NaOH to the salt solution. If it contains NH4 plus ions, right? This NaOH will react with NH4 plus, gives you ammonia. Okay, here there is no precipitation forming. Here you will see ammonia vapors forming. And then if you make a test for ammonia, that implies, and if you are getting a positive test for ammonia, that means the ion, the positive ion present in the solution is from group 1. Okay, so that's how you will decide it. Clear? Next, if you have the ions like Pb plus 2, Hg2 2 plus and Ag plus, any one of the ions is present in the solution, right? Then what we do is first we add dilute HCl to it. First we add dilute HCl to the solution. If on dilute HCl, if I see a white color PPT, then it could be either of these three ions. It could be Pb2 plus, Hg2 plus or Ag plus. And in that same solution, if there is no PPT forming, despite adding dilute HCl, there is no PPT forming, then you will add some amount of H2S into it. And after adding H2S, by chance, if you are getting any precipitate, it belongs to group 2. Group 2 is again subdivided as group 2A and group 2B. I'll tell you about that. Then we will try to discard this H2S. We'll try to remove this H2S by adding some concentrated HNO3 droplets. On adding that, whatever the sulfide ion which is present, it will take H plus and convert and come out as H2S vapors. Okay. And thereafter, you will be adding ammonium hydroxide with some excess amount of ammonium chloride. On adding this, we will be able to create a small concentration of OH minus. Obviously, you can see this is a buffer solution. And due to the common ion effect, NH4Cl is already present. Because of that, the dissociation of the base is very weak. So we will have very small composition of OH minus. Now with that small composition also, if there is a precipitate forming, that means it belongs to group 3. And group 3 will have these three ions. And if there is no precipitate forming here, you will, in the same solution, you will again proceed by adding small amount of H2S. Got it? And if you add some amount of H2S here, clear? And then you are getting a precipitate, it belongs to group 4. And in the same solution, if at all I'm not getting any precipitate, then you'll proceed to group 5 by adding ammonium carbonate. And by chance, if you get any precipitate of carbonates, that belongs to group 5. Even then, if you do not get any precipitate, then you'll directly discard all of this, right? You will take individual salt solution and directly make the reactions for checking the presence of Mg2 plus, Na plus, and K plus. Okay, this is a typical procedure. Now,
Yes.
see, group 1, these are the precipitates, and their chloride Ksp values are much lesser compared to the other metal ions. Group 2, you will have H2S added, so there is a small composition of S2 minus, and that might precipitate it. And group 3, like I said, hydroxides will precipitate. Group 4, again sulfides will precipitate, but with a slightly more concentration. Now notice this. In group 1, if at all we have these 3 ions, correct? What we do, first we take the original solution, that is the salt solution added with water, and then add it with dilute HCl. Okay. Acha, usually how to make original solution better? See, we take salt solution and add water. Dissolve हो गया बहुत ही अच्छा. अगर dissolve नहीं हुआ, if it is not getting dissolved, you will add dilute HCl. Even then, if it does not dissolve, you will add some concentrated HCl. Even then, if it is not dissolved, you will heat it. And by this time, most of the metal salts will get dissolved. Okay, and that is what we call it as original solution. Clear beta? And in that original solution, if you add some more amount of dilute HCl and you are able to see some white PPT here, it must be any of these 3. Now to differentiate these metal ions, what we do, we add small amount of water and boil it. Got it? We'll be adding small amount of water and then boiling it. On boiling, if still the residue is remaining, that means the precipitate is not getting dissolved. Probably it is HgCl2 and AgCl. If it is getting dissolved, it has to be Pb2 plus. Pb2 plus will get dissolved easily. And this is how you can separate Pb2 plus. Now, suppose if the residue is still present, then you add ammonium hydroxide and shake it. Okay. Out of which silver will start converting into a soluble complex, which is colorless. While mercury will form a black color PPT of this sort, Hg,
Yeah.
NH2, Cl plus Hg. Okay. Actually, this part is white, but this mercury part is black. So overall black will dominate it, make it the precipitate as black. Got it?
Yes.
And this amount will dissolve in aqua regia by boiling it. So have you noticed how we separated Pb2 plus, Ag plus, and Hg2 2 plus? Got it? Now, what are the chemical reactions that you need to know from Pb2 plus? See, Pb2 plus, usually when you react with dilute HCl, it will immediately become a white PPT. If you add excess of chloride, it will convert into a complex, soluble complex. If you add excess of H2S, it will become a black color PPT. If you add excess of ammonia, in ammonia, Pb2 plus does not form any complex. Pb2 plus will form PbOH twice, a white color PPT. Okay. With dilute H2SO4, it will become PbSO4. With H2S, PbS. With Ki, PbI2, which is yellow color. Okay. And this yellow color, when you react with excess of Ki, will convert into a complex K2 PbI4. Right. That's it. Okay. Clear beta. If you react with K2CrO4, it will give a yellow color PPT, PbCrO4. And that when you react with H plus, it will become Pb2 plus and CrO4 2 minus. With OH minus, it will become a precipitate and become CrO4 minus, CrO4 2 minus. Okay. With ammonia, it will only become a white PPT. With Na2SO3, it will become a white PPT of PbSO3. Carbonate will become a white PPT of both hydroxide and carbonate. Phosphate, it will become a white PPT. With KCN, it will become a white PPT. And in excess, there is no reaction. And with NaOH, it will become a white PPT. With excess, it will become a complex. Now this route is what NCRT has given. This is a very important route. This is a detection of Pb2 plus, correct? Other than that, which are the routes you need to learn? This is the route which you need to learn. I'll just mark it down. This one. This is the route you need to learn. This is the route you need to learn. Okay. What happens to the excess part here? And this is the route you need to learn. Clear? I guess Pb2 plus reactions are clear, beta. Right. Next. Hg2 2 plus. See, when it comes to Hg2 2 plus, what we need? Hg2 2 plus, when you react with dilute HCl, it will become white PPT. On adding excess amount of HCl, nothing will happen. With aqua regia, it will get dissolved into Hg2Cl2. With ammonia, it will become a black PPT. Just now we discussed, it will become Hg plus HgNH2Cl. With H2S also, it will become Hg plus HgS, a black PPT. In aqua regia, they will get dissolved, but the sulfide will become sulfur, which is black. Okay, sorry, this is white. Minus. This part is white colloidal form. Next, NO3 minus and NH3, if you react, you will get this form, which is white PPT. And with K2CrO4, it will become Hg2CrO4, which is a red color PPT. And on reaction with OH minus, this chromate will convert into chromate ions and Hg2O, which is a black PPT. With Ki, it will become Hg2I2, which is green PPT. With Ki excess, it will become a complex like this, HgI4, 2 minus and Hg black. And if Hg2I2 is boiled, then it will become HgI2 plus Hg. Okay. Now, likewise, there are other reactions. What is the main reaction that you need to learn from here is this one. Okay, I'll mark it again. One is this particular route you need to learn. Okay. How is it going towards HgI4 2 minus? Next, you need to learn this route. Got it? So, how is it becoming HgCl2? What will happen in aqua regia? And what will happen if you have an excess amount? Done? Yes. Next is Ag plus. In case of Ag plus, when you add it to dilute HCl, first you'll get a AgCl precipitate. If you add that to concentrated HCl, it will become a soluble salt, soluble complex. And that when you add it to water again, get back to its white PPT form. With cyanide also, it will become a complex here. Okay. With thiosulfate also, it will become a complex. With ammonia, it will become a complex. And when you add it with H2S, it will become a black color PPT of Ag2S. Got it. Next, with ammonia, initially it will become a black PPT Ag2O. With excess, it will convert into a soluble complex. With Cr2O7, first it will become a red PPT. Which on dilute with dilute HNO3, it will become this one Ag plus plus Cr2O7 2 minus. And if by chance you are adding ammonia, it will convert into CrO4 2 minus and complex formation. With Ki, it will become AgI. AgI, when you treat with cyanide, it will become AgCN2 minus. When you react with thiocyanide, you'll get this complex. With ammonia, no reaction. Very important. With ammonia, there is no reaction if it is AgI. AgCl will react, AgBr in concentrated ammonia will react, but AgI will not react at all. Because AgI's Kp value is much lower than the formation constant of the complexes for ammonia. While in this case, the formation constant of cyanide is much higher, thiosulfate is much higher compared to Kp value of iodide. Okay, clear beta? Right. Another route is this one with sodium hydrogen phosphate. You might get yellow color PPT. That on dilute HNO3 will get dissolved. With ammonia, it will form. It will also get dissolved, forming a complex. Okay. So here the route what you need to learn is this one is a very important route. What will happen here? Next one is the precipitation form, that AgI, how it is going to make different reactions here. and after that ammonia. With ammonia, what are the reactions? Yeah? These three are the parts you need to learn. Now, coming to the group 2 part here, see, in group 2, you might have all of this, okay, these ions, and they are trying to become sulfide precipitates. But here the problem is, within that, these precipitate can be categorized into two forms, 2A and 2B. 2A are the one which are insoluble precipitates in yellow ammonium sulfide. That means if at all I take yellow ammonium sulfide, they remain insoluble. But if you take these ions, right, then I mean these salts, they get dissolved in yellow ammonium sulfide. Okay. So if you are getting a soluble form, that is 2B. If you are remaining an insoluble form in ammonium sulfide, it is 2A. Okay. Mainly we need to learn 2A reactions and how do we categorize them. Check. What we do, if you are sure that there is a ion from a 2A, you will first add 50% of HNO3. Okay. In 50% of HNO3 concentration, most of the sulfides will get dissolved except for HGS. So HGS will not get dissolved, but rest of them will get dissolved. Okay. Rest of them includes lead, bismuth, copper, cadmium. These are the four which are present in group 2A. Okay. While HGS will remain insoluble. Got it? Now, what we do, if you take these ions here and add dilute H2SO4, okay, on adding dilute H2SO4, if there is a white PPT forming, it has to be lead because copper, cadmium, bismuth does not form sulfate precipitates. Got it? So you will get a PbSO4 white PPT, and PbSO4 usually get dissolved in ammonium acetate. Got it? And that is used as a test for Pb plus 2. Got it? On the other hand, if there is no precipitate forming, that means we will have bismuth, copper, and cadmium present, right? In that, you add NH4OH and filter it. And with NH4OH, if you are seeing a filter in which there is a complex formation, these are dissolved complexes. That includes copper ammonium sulfate or cadmium ammonium sulfate. Okay, you can separate that. If by chance there is no complex formation and it will remain as a white PPT, it will remain as a white PPT, then it has to be bismuth hydroxide. Got it? Because here bismuth sulfide will convert into bismuth hydroxide form here. Got it? Sorry, I mean bismuth nitrate, because we have already dissolved that sulfide into nitrate form, and that will convert into a bismuth hydroxide precipitate. Here, right? And now the filtrate which you have is copper nitrate and cadmium nitrate, isn't it? In that, again you add H2S. Again you add small amount of H2S. If you see a precipitate forming, it has to be cadmium. If there is no precipitate forming, the filtrate remains the same. That means it is of copper ammonium solution. Got it? This is how you will differentiate all of them. Hg2 2 plus, and here Pb2 plus, here bismuth 3 plus, and here cadmium and copper. You got the idea how to distinguish them? Now notice the reactions for Hg2 plus. If it is Hg2 plus, right? If you add dilute H2S, on adding H2S, first you will get a black PPT. And that when you add it with dilute HNO3, insoluble. If you add with Na2S, it will become a soluble complex. If you react with aqua regia, it will become a soluble mercury form and a colloidal sulfur formation. Okay. And if you react with Ki, we just learned this, it is the same thing. HgI2 will be forming. With excess of Ki, you will get HgI4 2 minus. HgI4 2 minus is what we call it as Nessler's reagent. This is called as Nessler's reagent. And that when you add it with NH4OH, it will become a complex of this kind, where you will have mercury as central atom. It is connected by two bridged atoms. The bridged atoms are oxygen and NH2. And that would have overall positive charge connected with ammonia, iodide with negative charge. And this is called iodide of Millen's base. Okay. It is a brown color precipitate which is forming here. This is a brown color precipitate which is formed. Clear? So this is the overall reaction. See, Hg2 plus Ki gives Hgi2. With excess, it will become Nessler's reagent, and that will turn into brown color precipitate. Clear? Uh, Another reaction you need to look at is cobalt 2 plus. If Hg is reacted with cobalt 2 plus and thiocyanide, then Hg will make a complex with thiocyanide and it will turn out to be deep blue precipitate. Got it? This will give deep blue precipitate. Hg2 plus tin chloride will give you Hg2Cl2 because tin is a good reducing agent. So tin will get oxidized to Sn plus 4 and Hg will get reduced to plus 2 to plus 1 first. And if you add further excess amount of SnCl2, this Hg plus will also convert into Hg0, which is gray black precipitate. Okay.
Yes.
Next, let's talk about bismuth. Hg2 plus is clear, beta. Right. Let's talk about bismuth. If you have bismuth plus 3 ions and if you treat with Ki, you will get BiI3, which is a black PPT. And that when you add it with excess of Ki will become an orange color complex solution, BiI4 minus. And that on adding with dilute water, it will convert into again BiI3, which was a black PPT, which on further heating will convert into BiOI, which is an orange color PPT. This is an orange color PPT. So this is the route which we need to understand how the bismuth plus 3 will convert into BiO3. This is an important route of figuring out the presence of Bi plus 3. Another route which you could notice is you react with NaOH. First it will become a white PPT of hydroxide. And that when you boil it, you will become this as BiO and OH, which is yellowish white PPT. And on adding few drops of peroxide, this will become BiO3 minus, which is yellowish brown solution. Okay. So these two are mainly used for confirmation of bismuth. Okay, rest of them you can use it, but not much asked in the syllabus wise. So mainly these two are the
Yes.
ones you need to learn. Correct?
Yes.
Next, check out copper 2 plus. Copper 2 plus, when you treat with H2S, first it will become a CUS precipitate. On adding with hot dilute HNO3, copper will get dissolved and sulfur, the what do you say, white colloidal form of sulfur is observed. With cyanide, it will become a complex releasing out S2 minus. And with sulfate, it will become copper hydroxide, copper sulfate, which is a blue color substance. And that on adding with excess amount of ammonia will convert into a deep blue solution. This deep blue solution is called as Switzer's solution. This is called Switzer's solution.
Mm. Yes.
Next, when you react with KCN, you will get yellow color PPT of cuprous cyanide. That on heating will convert into CuCN plus thiocyanate. Achha, even if you do not heat, at a prolonged time, it will get disproportionated to get CuCN and Cn twice. Got it? And this CuCN is a white color PPT, and this white color PPT, when you add it with excess amount of KCN, will convert into a dissolved colorless solution, which is K3CuCN, and that when you add it with H2S will not form any precipitate. Now, a complex which does not form a precipitate with any of the ions, that kind of complex is called as perfect complex. So this is forming a perfect complex which does not react with H2S again to form any precipitate. Okay. Next, copper 2 plus will also react with Fe CN4, CN6 4 minus. That means you have K4FeCN6. So for this complex, if you notice, copper 2 plus will connect, removing that potassium, and get a dark brown precipitate. You'll get a dark brown precipitate. And this dark brown precipitate, when you react with KCN, excess of KCN, it will convert into a blue color, you know, precipitate here. With ammonia, it will become a complex. Got it? Any doubt here, beta?
Yes.
Now, this reaction, whenever you have such kind of compound here, there are three major reactions that you'll notice with copper 2 plus. See, copper 2 plus, when you react with I minus also, it will, first you might expect ki CuI2 banega, but CuI2 is highly unstable. It will decompose into formation of Cu2I2 plus I2. Okay. And if you take this and add it to Ki, it will go an iodometric titration. That is, this iodine and Ki together will appear as a brown color, which is Ki3. If Cu2 plus is treated with KCN, you will get Cu. This is what you get, yellow one, but it is again unstable. It will decompose to form white PPT of Cu2 CN twice, and the other compound formed is CN twice alone. CN twice structure will be like this. Okay, is that I added somewhere here, structure here, thiocyanide. Okay, so this is CN and CN. So this is cyanogen gas. Clear? Now, instead of directly connected to nitrogen, if it is connected with sulfur, this is called as thiocyanogen gas. Like this is where I have written it. See, first you will get a black PPT, and that will decompose to get again a white PPT and SCN twice. SCN twice is called as thiocyanogen gas.
Yeah.
The connection is from sulfur and sulfur. So this is how it will be. Sulfur, sulfur gets connected to carbon, carbon connects it with nitrogen like this. Okay. Next, before approaching group 3, I told you one thing, that you will be adding some concentrated HNO3 to remove out the H2S if it is present. H2S is still present. To remove that H2S, we will be adding concentrated HNO3 droplets. Okay. Here, see, add concentrated HNO3 first. What will it do? It will boil off H2S. Okay. Second thing, while boiling off, any Fe plus 2 present, right? That will be converted into Fe plus 3, because Fe plus 2, right? If you notice Fe plus 2, there is no test for Fe plus 2 in salt analysis. We have only test for Fe plus 3. Got it? That is why we will always try to figure out for Fe plus 3 only. Got it? Check. With oxidation of Fe plus 2, we will get Fe plus 3 here. Now, then you will be adding ammonium hydroxide and NH4Cl. On adding this amount, if there is any PPT forming, it means it could be either ferric hydroxide, aluminum hydroxide, or chromic hydroxide. Ferric will be reddish brown, aluminum is white, chromium is green. If there is no precipitate, you'll proceed to group 4. And now you add another 2 droplets of NaOH, right? If the soluble remains, if the precipitate remains insoluble, it has to be either ferric hydroxide or chromium hydroxide. Okay. And if there is a complex forming and it is a soluble form, that has to be aluminum. So NaAlO2 is a soluble form here. Got it? And this is a confirmation for the presence of Al plus 3. Now, out of these two precipitates, if we add some bromine water and KOH, bromine water and KOH, if it remains insoluble, it means it is of iron. And if it becomes soluble, it is of chromium. Right? Because chromium will get dissolved with bromine water, because bromine water is an oxidizing agent. That will oxidize this Cr plus 3 into Cr plus 6, which is K2CrO4, yellow color solution. Okay, clear beta?
Yes.
And now this soluble form of sodium aluminate, if you add it to water, it will again regain back aluminum hydroxide. And if you heat further, it will become an anhydrous Al2O3, which is also known as bauxite. Clear? One
Yes.
short understanding you should have is, if you combine a Fe plus 2 salt with an Fe plus 2 salt and you're getting a precipitate or a complex, it will be white in color. Okay.
Yes.
If I combine Fe plus 2 and Fe plus 3, it will always be blue in color. And if you combine Fe plus 3 and Fe plus 3, it will always be brown in color. Got it? So just keep this in mind. What are the colors for various metal ions? Okay. Now notice here, if you have Fe plus 3 and you react with ammonia there is no complex formation here. It will remain as ammonium hydroxide. Okay. And that ammonium hydroxide, which is reddish brown, which on strong heating will convert into Fe2O3, or with excessive amount of ammonia, no reaction here. Okay. And if
Yes.
you take with NaOH, it will remain with excess of NaOH, no dissolution. Got it? With ammonium sulfide, it will become FeS precipitate, a black color precipitate, and sulfide will get separated out. Now with KCN, it will become FeCN thrice, which is a brown color substance. With KCN, it will become a complex, which is yellow color.
Yes.
Next, Fe plus 3 and Fe plus 2. Here it is Fe plus 2. That will become Fe4, FeCN6 thrice. Done. Now this is a blue PPT, which is called as Prussian blue. This is a Prussian blue PPT. Hmm? And now this PPT, if you add it with NaOH, it will become a reddish brown. I mean, it will get back to the original hydroxide form. If you react with oxalic acid, it will remain blue color, but as a solution. With concentrated HCl, it will get decomposed. With dilute HCl, it will remain insoluble. Now, this is the main route for iron. Got it? This is the main route for iron. So, please learn it properly. Okay. Now, other than that, like I said, this is plus 3, and you are again reacting with a plus 3 complex. Plus 3 will give you brown. You can see Fe, FeCN6. So, it is a brown color solution. And that when you react with peroxide, one of them, which is sorry, SnCl2, one of the iron will get reduced and convert that into blue color precipitate again. Clear? And with ammonium or potassium thiocyanide, it will become a complex which is deep red color solution. Okay. And you can showcase that complex in the form of FeSCN thrice, or you can showcase as FeSCN overall plus, or FeSCN6 overall plus 3. So in all these cases, it will have uh, red color solution in either this form, or this form. Got it? Lastly, if you take it with acetate, we use this as a test for acetate. So it will become a reddish brown solution of this one, 3 to 6. Okay. So remember like this, 3 to the 6. Clear? So iron would have 3, hydroxide will be 2, acetate will be 6. Okay. Tanya, clear beta?
Yes.
So this we have already learned. Okay. Red color, uh, blood red color, you will keep on getting this reaction multiple times. This is the main reaction that you need to learn. Got it? From Fe plus 3. Next with Al plus 3. See, Al plus 3 also, when it comes to ammonia, it does not form any complex. So if you add ammonium chloride with ammonia, it will remain hydroxide, and with excess amount, nothing will happen. But in NaOH, it will get dissolved. First, gelatinous white PVT will form, and excess amount, if you add, it will get dissolved. Got it? Now, apart of that, one more reaction where you need to notice here is this one, Al plus 3, when you react with NH4Cl. Okay, NH4Cl. First, you'll get a white gelatinous precipitate. With dilute HCl, it will become dissolved AlCl3, which is colorless solution. And then we react with a compound called alizarin and adding ammonia drop by drop. You will see a red color complex forming on the surface. And this is called red lake. Okay. And this is a confirmatory test for aluminum as well. So these two are important ones, how you get this side and how you get towards this side. Clear? Chromium plus 3. See, chromium plus 3, if you react with ammonia, first you will get CrOH thrice, which is a gray color solution. A gray-green color solution. And then with excess amount of ammonia, it will become a complex. Got it? And
Yes.
on the other hand, if you react with any strong oxidizing agent, okay, sorry, mild oxidizing agent like peroxide, bromine NaOH, you know, S2OA2 minus, these are mild oxidizing agents. So in the presence of Cr plus 3 with these oxidizing agents, it will get oxidized to Cr or CrO4 2 minus. And CrO4 2 minus, which is yellow color solution, that when you react with barium 2 plus, it will become barium chromate. And with dilute H2SO4 and amyl alcohol ether, you'll get CrO5, a butterfly type of a structure, which is blue color solution. Okay.
Yes.
Now this is the main route for identification of chromium plus 3 reactions. If you are getting a chromate solution, we could always add lead acetate to convert into a yellow color PPT. And this with excess of OH minus does not get dissolved. Saniya clear beta? Right. This is a reaction for chromium. Now let's talk about zinc. That means if there is no precipitate forming, we will come towards group 4 here. Now in group 4, what are the ions you are trying to precipitate? Zinc, manganese, nickel, and cobalt. These are the ions you are looking for. Now, what you do, you would add NH4OH excess, along with that pass some amount of H2S. Now you do notice that if you have NH4OH present in the solution and if you react with H2S, H2S is a acid and that is a base. So we can expect some amount of ammonium ions plus H2O plus S2 minus, correct? So the S2 minus concentration will increase. This S2 minus concentration will increase as you add more amount of NH4OH. That's why if you have an increased concentration of S2 minus and then you are noticing a PPT, that means it has to be either zinc, manganese, nickel, or cobalt. Got it? And what are the colors? White PPT, pink, yellow, pink, light pink, black, and black. Now, if a PPT has come, then you add some amount of dilute HCl and shake it again. If at all this precipitates get dissolved in HCl, then it has to be manganese and zinc because they are the ones which will get dissolved to form chlorides here. Okay. And if they are not getting dissolved and they remain as a black precipitates only, as a sulfides only, correct? Then that has to be cobalt and nickel. Thereafter, you would add aqua regia to this solution. Aqua regia is 1 is to 3 ratio, molar ratio of HNO3 and HCl. Okay. On adding this, you would get this COS and NIS get dissolved. And in a dissolved form, they will have a colored solution. If COCl3, COCl2 is formed here, correct? It will turn pink in water. I mean, first it will become a blue residue, which will turn pink in water. And this is a yellow color residue, which will turn green in water. Okay. You might wonder what is this, green color here. So basically, this will be like cobalt, H2O6, 2 plus. And here it is nickel in water This one, nickel, H2O6, 2 plus. This is that green color. Here, this is this pink color. Okay, right. Next, cobalt plus 2, which is in a pink color now. We take one part we can add it with ammonium hydroxide, acetate, and KNO2. Okay. On doing that, if at all you are getting a yellow color PPT, if you are getting a yellow color PPT, this is the one, K4CONO2 6. Basically, it will start with this one, but eventually it will end up forming this precipitate. K4 cobalt nitrate 6. Okay, beta. The second part, when you react with ammonium thiocyanate with amyl alcohol, it will give a blue color layer in alcohol. Okay, but this is rarely used. For cobalt, we'll always use this part to get that yellow color PPT. Done. For nickel case, if this complex we add with NH4OH excess and DMG, okay, DMG is this kind of structure, dimethyl glyoxymeto. Okay, so if we take the DMG, that will turn into rosy red color by formation of this nickel DMG precipitate. How does it look like? This is the structure it looks like. Nickel is surrounded by lone pairs of all four nitrogens. This is one DMG. This is the other. This is the other DMG. Okay. More about the details of DMG we'll learn in coordination. Okay. Now, if the filtrate is being boiled, if the filtrate is boiled, just to remove in case if there is an H2S, and then add bromine water NaOH again. Bromine water NaOH will oxidize the manganese into Mn plus 4. That is, it will become MnO2, a black color PPT, but zinc will remain dissolved form only. So it will remain the filtrate form, but this will become a PPT. And in that PPT, if you add dilute HNO3 by adding PbO2, it will become more oxidized and convert into HMnO4, which is purple color solution. Okay. And which on passing with H2S will convert into white PPT of zinc sulfide. Next, if there is no PPT, we can see there is a zinc formation, and zinc can be divided into two parts. One part you add it with acetic acid with K4FeCN6. Then if this potassium is been replaced by zinc here, correct? So zinc will come this way. It is a white color PPT. This is a white color PPT. And if you add excess amount of K4FeCN6, then it will convert into a light blue PPT, which is K3Zn twice FeCN6 whole times of 6. Done. Now this is one important confirmatory test for zinc. Saniya, clear beta? Right. For nickel, the typical reactions are these two, which you need to check. With ammonia, it will become a green PPT. And that when you add it with ammonia, it will give a deep blue solution. It will give deep blue solution, right? And this, when you react with DMG, this is the DMG, will get a rosy red precipitate. Okay. Cobalt, when you react with ammonia and NO3 minus, you'll get a blue color precipitate with on. If this has been treated with ammonia, then this is the yellow brown solution which is formed. And next, if you treat with K3 cobalt nitrate, which is yellow color PPT, clear? This is the confirmation for cobalt, which we learned. Any issue here, beta?
Understood.
Right. See for manganese now. When it comes to manganese, with ammonia, it will become a white PPT. And if you expose it to air, it will become a brown PPT by taking a nascent oxygen. With NaOH, it will become a white PPT with excess of NaOH, no dissolution, exposure of air. This is the brown PPT which is formed. Okay. Zinc with NaOH white PPT. In excess of NaOH, it will get dissolved to form this complex. With ammonia, it will become a complex. With K4FeCN6, with little, we'll get this white color PPT. And this PPT will have variable composition depending upon how much amount you are adding. Okay. With K3 cobalt cyanide here, which is yellow color. Now this will convert into an aqueous form, which on ignition, because once you have a cobalt form and a zinc form together, it will become a Rinmann's green. This we learned in dry test. Suppose if it is still not giving you any precipitate form here, still we are not getting any precipitate form, then you will boil off H2S, again add ammonium carbonate this time. Got it? We'll be adding ammonium carbonate. On adding ammonium carbonate, if at all I'm getting a white color PPT, it has to be either of these three: barium carbonate, strontium carbonate, or calcium carbonate. Clear? And if there is a filtrate forming, I mean, if there is no precipitate forming, you will move on to the next group here. Clear? And if these white PPTs are dissolved in acetic acid, right, and then you differentiate, I mean, then you separate into three parts here. First part is react with K2CrO4. If you get a yellow color precipitate, which is soluble in ammonium, soluble in acetic acid, this has to be barium 2 plus, because barium's Ksp value is low for chromate value. So you can see the solubility of chromate is less here. So calcium and strontium will still appear as a soluble form of chromate, but barium will remain as precipitate. Second, if you react with ammonium sulfate and you get a white PPT, and that get dissolved on addition of HCl, that has to be strontium. That is a confirmation for strontium. And if you take ammonium oxalate and it will become a white PPT, then it has to be calcium oxalate. And calcium oxalate with acetic acid get completely into a dissolved form. Correct? So these are the confirmation for calcium, barium, and strontium. Okay. Even after this also, if you're not getting a PPT, then definitely you're supposed to look into every ion individually, starting with Mg+2. Okay. For Mg+2, what are the reactions you will do? If you are sure that there might be magnesium present, first you will treat with ammonium chloride and ammonia, okay, to give a small composition of hydroxide. So there might be some amount of hydroxide forming, and this will react with Na2HPO4. So basically you add it with sodium hydrogen phosphate. On adding with sodium hydrogen phosphate here, it will become magnesium ammonium phosphate. This will become magnesium ammonium phosphate. Magnesium ammonium phosphate is a white color precipitate, and that is soluble in acetic acid or any mineral acids. In fact, this white PPT, if you if you heat it completely, this will remain another white PPT, which is Mg2P2O7. Clear?
Yes.
Right. Next. If you are checking out for NH4 plus, that is zero group, right? Then with NH4 plus, the best thing to do is this Nessler's reagent. You add to Nessler's reagent K2HgI4. It will become brown color PPT, which is of Millen's base, isn't it? If you treat that with, Na3, this one, you will get a yellow color PPT, because this is a soluble form, but this is a yellow color PPT. With H2PtCl6, this will also give yellow color. Achha, here the problem is one thing. If potassium K plus is there, K plus will also give you the same yellow and same yellow here. The way to differentiate is this one. Potassium cannot give this brown color precipitate. So it has to be ammonium only. Got it? Test for potassium is simple. If you take any salt of potassium, you react with this sodium cobalt nitrate salt, you'll get a yellow color PPT of K3 cobalt nitrate. Okay. If you want to predict what is about sodium, got it? What's with sodium? Then you can see KH2SbO4 with NaCl, and you'll see NaH2SbO4, which is a white color PPT. And this PPT is like a confirmation for sodium. Clear, beta? Only barium, if you want to confirm, what are the confirmatory tests for barium? First, with dilute H2SO4, it will become a white color PPT, and this is insoluble in HCl. So white color PPT, if you add dilute HCl, it will remain insoluble form. But if you react with concentrated Na2CO3, it will boil off the sulfate form and convert itself into carbonate precipitate. Strontium, when you react with dilute H2SO4, become SRSO4. It is insoluble in ammonium sulfate, okay, but soluble in boiling concentrated HCl. And thereafter, you react with concentrated Na2CO3, and then you will get this as SrCO3, which is a white color PPT here. Is this clear? With calcium, you will see calcium plus oxalate will become calcium oxalate, which is white color PPT as well. Okay. That's it. These are the ones which we need to know from wet test beta. Got it? Now, most of the compounds here, if you notice, I have written it this way for, practicing. Clear? So you would practice Pb plus 2 in this manner. Check out all the reactions. Ag plus, write out all the reactions and practice this way. Hg2 plus, got it? Similarly, you can practice it for copper and other ions as well. Okay. Now, this is a part which you need to know it from uh, salt analysis. Now, there are two assignments which I have added for salt analysis. Just a minute.